Okay, so suppose that I wanted to do differential equations instead of physics homework. First thing. Okay, so to do number 41 and 2.1, I think I need to recall what this object is before I start. So far I have y prime plus 2x over 1 plus x squared times y is e to the x over 1 plus x squared quantity squared, and they tell me that y of 0 is 1. Okay? So what kind of beast is this, first off? Okay, it's first order, non-homogeneous, linear. Okay, all that stuff. All right, so what is my procedure for solving first order non-homogeneous linear differential equations? First things first, do the dumbest thing you can and pretend it's homogeneous. Okay, so what does the homogeneous version look like here? So I got y prime plus 2x over 1 plus x squared y equals 0 instead. Do I need to worry about the initial condition?
Not yet.
Definitely not yet. Okay. What's that?
The subscripts.
Oh yeah, and I probably should think, right? Really, this is the homogeneous version that I'm solving, so those aren't y's, they're different. Cool, thank you. Okay, so then what? How do you solve first order linear homogeneous differential equations?
You can apply the formula here.
Yeah. Cram this in the formula. So to cram this in the formula, what do you need to identify?
P of x.
Yeah, you just need to identify the coefficient function. That would be this fellow here. That's p of x, right? So this would tell you that yh is, what's the form for this? Yeah, some constant e to the negative antiderivative of O of that thing, right? We got 2x over 1 plus x squared dx. Okay. Which is, how do you do that integral? U substitution. So you let u be what?
That's x 1 plus x squared.
Either one. Yeah, 1.
Let's go with 1 plus x squared to save ourselves the trouble of doing a double u substitution. Double u substitution. Not a double u substitution, but a second u substitution. Cool. All right, so du is then 2x dx, and we're all hopefully bored to death by doing this. So that's your du. So you have a e to the minus integral of what? 1 over u du. Okay, so you get out of this a e to the minus natural log of the absolute value of 1 plus x squared. Really, plus a constant, right?
Yeah.
But I already kind of got the plus a constant in the x, so you don't need to sweat that here.
Why did the absolute value lines come in there? Is it just like how that is, or?
Yeah, the integral of 1 over u is the absolute value, the natural log of the absolute value of the thing. The good news is here that they're totally redundant, because 1 plus x squared is positive. Okay, so dump those, because who needs that shit?
And we just dumped it on the other side too, right?
Totally.
Okay.
I'm just ignoring the plus or minus. Really, that's in the a. Right, I already kind of went through this formula, like.
You can
I
simplify.
remember.
You should simplify it a little bit.
And now I should simplify a little bit by whatting?
Well, a log rule.
Even the natural log of something is something, since you have a negative up there, it would be 1 over that something.
Perfect. So use a log rule to drag this -1 coefficient up here as a power, and then the e and the log are inverse functions, so they undo each other. So in the end here you get a over 1 plus x squared. False.
Didn't you say we could make A always 1 by taking the constant to be 0?
Totally. And what you definitely should do, since you're just going to use this to find the particular solution anyway, right? Since you're just going to go trot this into the non-homogeneous equation, you should pick A as 1. Right. So this makes a very particular YH, which is 1 over 1 plus x squared. And then I'm going to forget that that's the particular one, and I'm going to just call that YH. Guys cool with that? It should be noted that that's actually a particular choice, but all I'm using this for is variation of parameters anyway. So it doesn't really matter. Guys cool with that? Okay, what do I do with this information now? So now that I solved the homogeneous equation,
There's actually another formula
Derivative
for
of the homogeneous.
generate your y.
yeah, you should generate a better guess, right? You guys with me? So your better guess should be that you need to, okay, so what's my better guess for y?
U of x.
U of x times y.
Yeah, so some u of x divided by 1 plus x squared. Right, and now I need to take the derivative of that.
They gave us a formula in the book for that?
Yeah, I don't care.
Can
I
we,
can't
like
remember.
on a test, can we just fire that in there?
Sure. Yeah, if you guys can remember it, go for it. I'm too dumb to remember it, so I just remember how it works. So, what's your y prime? Quotient rule that stuff? No, yeah, product rule it, because you know you're going to see the homogeneous equation, right?
Yeah.
So it's probably a much better idea to product rule it so the right stuff cancels, because otherwise you'll have to do a bunch of friggin' algebra to find it. Okay, so product rule that stuff. So this is a product rule between u of x and 1 plus x squared to the minus 1 power, right? So the derivative of the first thing is u prime, right? Times the second thing. So 1 plus x squared to the minus 1. And then plus u of x, right? Times minus 1. Yeah, and then all this crap's going to cancel anyway, so. But just to be totally on board here, it's that stuff. And then what do you do with that thing? Yeah, go trot that into the original equation. So if I plug this junk in the original equation, I have u prime 1 plus x squared to the minus 1 power plus some junk that's going to cancel. U of x times minus 2x 1 plus x squared to the minus 2 plus 2x over 1 plus x squared times what? Yeah, my guess for y, which was u and then 1 over, so I got u of x over 1 plus x squared. Hey look, that cancels. Fully by design, right? And all of this equals e to the x over 1 plus x squared squared. Cool?
Yeah.
Yeah?
Yeah.
Okay. So in the end here I got u prime, u prime over 1 plus x squared is e to the x over 1 plus x squared. Squared. And now what?
You multiply both sides by 1 plus x squared and integrate.
Okay, so if we multiply both sides by 1 plus x squared, we get this. And so we find out that u prime, how about du dx, right? U prime is e to the x over 1 plus x squared. And at this point, I see what Anthony was whining about. Yeah, So does anybody else see what Anthony was whining about?
Yeah.
What was he whining about?
We can't do that.
Yeah, that's an integral without a closed form, right?
There's a formula.
Correct. Do this. U of x is what?
The integral of
That
that.
integral.
Yeah, it's the integral of that. Cool. Is that the answer I wanted to hear? No. Might I try for a minute to integrate that? Y'all are lazy. Yes, you would try to integrate that for like a hot
5 minutes.
2 or 3 minutes, maybe.
Integration by parts didn't take all that long. One line.
Still work?
Yeah.
What?
I
think I did it too.
All right, let's try it. Man says it works.
I'll let you guys try.
Is that to the negative?
We could try plugging it into
The computer and see, because if there's no answer, you know.
No, it's cool. Let's see if it works. Fella could be right. Integration by parts is actually a great idea.
Oh, no, it's
No, it's a good idea.
As long as you keep 1 plus x squared on the u side and just, keep on integrating e to the x, eventually you'll get to the end of it.
I think that the 1 plus x
No.
squared is.
What did that, just keep repeating that?
Yeah.
Yeah.
Because you can't keep on differentiating 1 plus x squared.
You can go forever on that.
Okay, so if I was to try u substitution, and I think this is a good idea, let's try it. So I get to pick 2 things, right? Integration by parts. When I do integration by parts, I get to pick 2 things. What are they?
One thing to differentiate, one thing to integrate.
I get to pick 1 thing to differentiate, 1 thing to integrate. Right? Okay, on this, you could pick that either way, actually.
No, because you keep on integrating 1 plus x squared, it does that. But if you put 1 plus x squared as u, and then differentiate that, well, you just keep on integrating e to the x, then it doesn't matter.
I think they're both going to be a problem. So what's your plan? Which one should I pick?
1 plus x squared for u.
1 plus x squared can't be. Integration by parts, you need a product of 2 things.
Well, there's like the
I can do 1 over 1 plus x squared.
Never mind, I see where we're
Yeah.
Side. Okay. So my 2 options are that I need to pick something to differentiate and something to integrate. So I might pick 1 over 1 plus x squared as I'm going to differentiate this thing. And if I keep differentiating this, it's going to get what? This is going to get worse and worse, right? And I remember there's this weird thing about integration by parts, like sometimes it comes back around. You guys all remember that trick? There's that like around the corner trick for integration by parts. But this thing ain't going to come back around. Right? Because you're never going to get another one of those again. When you differentiate this, like your du then is going to be what?
negative 1. That the square root of 1.
Negative 2x over 1 plus x squared. Right? And then over here you'll pick a dv, right? And your dv will be e to the x. Well, e to the x dx, right? And then you'll get a e to the x for your v. Oh, and this guy needs a dx. Bye. You guys cool with this? And then you plug this in the integration by parts formula, and you figure out that maybe u of x is also uv minus the integral of what? v du. Okay, cool.
I was wrong.
It wasn't a bad idea. It was a really good idea, actually. It just, yeah, integration by parts has that multiplication built into it. If we had had an e to the x times a 1 plus x squared, awesome. Hit it twice with integration by parts, so kill it off. Got it, done. Sweet. The cool thing about this is you could try it the other way. Because you guys know how to integrate 1 over 1 plus x squared. Right?
Natural law stuff.
So if you tried it the other way, you'd let u be e to the x, then du is e to the x dx, right? Your dv would have to be 1 over 1 plus x squared dx. What's v then?
Natural log absolute value.
No.
Oh, no,
Isn't
it's
or whatever.
inverse tan, right?
Yeah, that's arctangent. And so you could rewrite this again as, let's see, uv e to the x arctangent of x minus the integral of v du arctangent of x times e to the x dx.
That's easy.
Yeah, and that's of course a known right? No. Right, so you might try that with integration by parts. And of course, the only obvious solution for, or the only obvious way to try this with integration by parts would be to let this be u so that you can differentiate it and let that be v. But why is that a really dumb idea?
So you're gonna go back to cancel.
Yeah, because you'll just go back to where you were before. You'll just have taken a long time to do it. You guys see that? Like, there's a horrible circle you could draw on the board with math. Cool. So I don't know how to do this, so I'm going to leave this the way it is. So I'm going to let my u be that integral, and I'll just leave it in that form. That happens sometimes.
If we were really ambitious about that, could we change it to a different coordinate system and actually kind of screw up that?
If you really needed this for something, the way we will have a technique that will do this later.
Okay.
Still not in quite a convenient way. Like, this thing doesn't have a convenient closed form. Sorry, sometimes that happens. This happens especially if you're doing like real world application, like physics problems. You often are left with one of these integrals that there's no closed form for. That.
They give you the initial conditions, so do you put the constant in there, solve for your constant at least?
Yeah, I think we can do just a little bit with the initial condition, right? So they told me what u was, or sorry, they told me what y is at 0, right? And what I know is, I know what u is, and I have my homogeneous solution is here, right? You guys see that?
Yeah.
So I think my end here is that, all right, I know what y of x is basically. It's 1 over 1 plus x squared times the integral of e to the x over 1 plus x squared dx. Do you suck that 1 over x squared into the... No, that would be really silly. Okay. Be a little careful with these. Sometimes your little algebra brain kicks in and you like start simplifying even though it didn't make any sense to pull that in. But I think I can do a little bit with this initial condition. What should y of 0 be? I think I got 1 over 1 times
Integral of 1 over 1?
the integral of 1.
It's just x. Right?
Wouldn't that,
Well, this is a function, right? So this is a little bit bizarre. You guys see that? Like I just said we couldn't put this in there, so why did I just evaluate that crap at 0? You guys see that? So I think I'm a little troubled on even doing.
You'd have to integrate.
Well,
first,
wait, but then you
multiply.
integrate and you get a constant at the end and.
Yeah. You guys with that?
Like your initial
So-
condition will tell you what the constant is.
I'm going to integrate this, right? I'm going to get some function. Let me call it, say, f of x. Then I'm going to evaluate that function at 0. So that should really be 0. And then I should have some constant c, right? You guys see that? But this was supposed to be 1. So I think I know that 1 is supposed to be f of 0 plus a constant, right? You guys see that? But I don't really know what the function f was. This is about the best I can do. You guys with me on that?
So would you leave it like that, or would you say like f of 0 is either 0 and c is equal to 1, or c is equal to 0 and f of 0 is equal to 1? Like, would you want us to write something like that? Or?
I mean, maybe the best way to write it would be to say c is 1 minus f of 0, right? You guys do that?
Yeah, whatever I'm doing.
I think I would probably lean towards you guys writing this with y of 0 is 1. Right? Because that's going to depend on what you get out of that function.
I was wondering if you write that integral as c plus the interval you got there. and
If
then
I write, oh, this guy?
Yeah, the c plus the integral, okay? Now I'm going to integrate that from 0 to 0, so the integral part goes away, and you're left with c equals 1. Because that can be evaluated because you're doing it at 0, so you're actually integrating from 0 to 0, which is 0.
But when we have 0
Because that's your initial
No, you
condition.
should see.
You're going to evaluate your integral from
Yeah, that's, if that were fixed, yeah.
Unfortunately, I don't think that's the case. Let me try an easy example. Like, let me highlight my thought process. So, the thing I'm worried about is that the function that I get out of that integral might not be 0, right? So let me propose a similar problem and see if it would work when I could actually do this integration, right? So similar problem, I'm just going to say, let me suppose y of 0 is 1, right? Same initial condition. And then let me suppose that the function I got was easier. Let me suppose the function I got was the integral of e to the x dx. Like, and just for whatever reason, I felt like I was having a brain fart, so I wrote this down and I just couldn't do it. You guys see that? And I was like, okay, so if I plug, so y of 0 is 1, and then the claim would be that this should be the constant out of that, right? Because you're saying, okay, so we integrate from 0 to 0, e to the x, and then we'd get this constant. So our c should be 1, right? You guys see that? But if I actually do this integration, what do I get? I get y of x is e to the x plus a constant, right? And then I plug 0 in, and I get y of 0, right? 1 is, well, 1 plus a constant. So I find that the constant has to be 0 in this case. So what's going on there is that this integral doesn't have bounds on it. You're not integrating from 0 to x. You're taking an arbitrary antiderivative, right? There's no guarantee that when you take an arbitrary antiderivative and evaluate at 0, you get 0 out. So I think the best you can do is this. Like, your y of x is your homogeneous solution times the u you got out of variation of parameters, and there's some initial condition that's true.
In the book, it looks like they used one of the.
They use a table trick or something?
Well, they went integral from 0 to x of e to the t 1 over 1 plus t squared.
Oh yeah, they just made
It's
a.
the same.
Yeah, they cheated a little bit. So there is another thing you could do, which is you could say, okay, I was asked about x's, right? So what if I was willing to force something silly, like I know a function that has this thing as its antiderivative from the second part of the fundamental theorem of calculus. In my opinion, this is a dumb trick, but it's a valid trick. So let's spend a second. So what you could do is you could say, okay, I know one function that differentiates to that. So I'm going to propose that the antiderivative of e to the x over 1 plus x squared dx is in fact the integral from 0 to x of e to the x over 1 plus x squared.
E to the t, maybe.
Sorry, d. If I put t's in here, it'll make everything clearer. You're right. So if I do the integral from 0 to x of e to the t over 1 plus t squared dt, right?
Right.
Now if I take a derivative with respect to x, I know exactly what I get. I get this thing.
Yeah.
Cool? So now they said, if I do this, now I know what the constant is.
That's good.
You guys see that? Like, now I can figure out what the constant is. The constant has to be 1. This is just a dirty trick. And part of the, I'm not a fan of this because I think if I wanted to find the constant, the right way to do it would be to actually calculate this antiderivative, right?
Yeah, at least numerically.
Yeah, at least numerically. And then, of course, you would plug in y as 0 to calibrate your numerical approximation. This is not mathematically invalid. It's just a dirty trick.
We could technically put it in series.
Yeah, and that's what I was saying. Like, later we'll have a technique to do this. And the technique we'll use to do this is we'll write a Taylor polynomial for everything involved. Right? And then we'll just have a Taylor polynomial, and a Taylor polynomial is a function, so we could be done. And then we'll have to worry about like radii of convergence and all sorts of other weird crap. Cool? That help at least confuse the heck out of you? Okay.